In the silver nitrate test, we will be using acetic acid, phenol, aniline, and benzoic acid as the reagents or test subjects. Here we simply add a few drops of the reagent along with a good quantity of ethanol. Finally, we add a small amount of 2% ethanolic silver nitrate and it is done. The formation of precipitates indicate that our sample is acidic. And well, if you do wish to dissolve the precipitate, adding some 5% nitric acid will do the job. Here we see the results. No reaction with phenol and aniline, other than slightly messing up the appearances, that is, and with acetic acid and benzoic acid, it tested positive for acidity. Well, who would have figured that out? Wasn't quite obvious with the name, wasn't it? Formation of precipitates occurred and addition of nitric acid dissolved it away. Here we see the result of our experiment. The precipitate that we noted was, as what the test says, silver acetylide. Okay, so here's a fun fact about what we just synthesized. Just like acetylene, silver acetylide is also a heat and shock sensitive explosive. When it is detonated, you'll notice that there is no evolution of gas as it is only composed of silver and carbon. Same precautions as acetylene should be made, otherwise this will literally blow you away. Back to discussion. Now we define acidity and basicity. Acidity, based on the Bronsted-Lowry concept, simply says that it is the capability of a compound to donate a proton. Acidity is usually associated with the functional groups containing the hydroxide ion, like alcohols or carboxylic acids. As for basicity, based on the Lewis concept, is the ability of a compound to donate an electron pair. Basicity is usually associated with amines, since the nitrogen is capable of sharing a lone pair. Here's the mechanism for our silver nitrate test earlier. What simply happens is that the hydrogen in the hydroxide part of the carboxylic acid is replaced by silver upon the addition of silver nitrate. Since this is in equilibrium, both the left-hand side and the right-hand side of the reaction are present at the same time, which is the reason why we see the precipitate. Addition of nitric acid simply causes this to shift to the left, as stated in the Chatelier's principle. That's why the precipitate solves. So now here's a summary for the silver nitrate test. This test was designed to detect strong acids like carboxylic acids because of the presence of precipitates indicating replacement of hydrogen atoms. The reaction that occurs precipitates the salts of the carboxylic acids, and as said earlier, adding nitric acid will dissolve the said precipitates. Now we see the mechanism for the formation of the silver acetylide. Acetylene is combined with Tollens reagent. The hydrogen from the acetylene will be substituted with the silver from the Tollens reagent, and no bonds are broken. The result is that we have silver acetylide in a nitric acid solution. This reaction is general for most, if not all, alkynes. Here we have a summary for the silver acetylide test. Substitution reactions like these are present only in alkynes. It does not exist in alkenes. This property enables one to differentiate acetylene and ethylene. When acetylene is passed through Tollens reagent or cuprous chloride, formation of silver acetylide or cuprous acetylide occur respectively. Now we are done with acidity and basicity. Lastly, we test for alkyl halides. Our first test is the alcoholic silver nitrate test, and our reagents will be ethyl chloride, ethyl bromide, ethyl iodide, benzyl chloride, tert-butyl chloride, sec-butyl chloride, and chlorobenzene. The process is to add some alcoholic silver nitrate in a test tube along with a few drops of any of the reagents. The test tube is shaken, heated in a water bath, and done. What we are observing here is the formation of the precipitates and their colors. The results for the experiment are here, each reagent giving a specific color of a precipitate, indicating which halogen is present. Note though that no reaction occurred with chlorobenzene. Here we define alkyl halides as a group of chemical compounds consisting of alkanes with halogens bonded to them, making them organic halides. This is the general mechanism for the experiment performed. An alkyl halide is combined with silver nitrate. The halogen is simply replaced with the nitro group from the silver nitrate, and the halogen takes the place of the leaving compound. Thus, the result is an organonitrate and a silver halide. Here's a summary for the tests for the alkyl halides. The test is used to differentiate aryl halides from alkyl halides, seeing as aryl halides are unreactive in the test. Alkyl halides that react form silver halides that are insoluble in nitric acid. The reaction usually occurs slowly, so a little heating may be necessary. Since this is an SN1 type of reaction, tertiary halides are favored over secondary halides, which in turn are favored over primary halides. On a side note, alkyl bromides and iodides react more rapidly than chlorides. We're finally done with all the tests. Now let's tackle the guide questions in the experiment. So, what tests could be used to differentiate saturated and unsaturated hydrocarbons? Explain how the test could differentiate them. Well, as said earlier, we can test unsaturation using the bromine in methylene chloride solution, or the Bayer's test. In the bromine test, you get a positive result with the loss of the red coloration, which is due to bromine bonding onto the sites where the pi bonds are broken. Remember that unsubstituted aromatic compounds give negative results. In the Bayer's test, a positive result means the removal of the purple color, which is due to hydroxide ions bonding on the broken pi bond sites. Note that alkanes and aromatic compounds do not react here. Next, do alkynes give all tests which alkenes exhibit? What tests could be used to differentiate them? Well, we know that it is difficult to differentiate the two because both give off the same results. Usually, only terminal alkynes can be differentiated easily by letting them form methyl derivatives. Reacting them with a basic iodine reagent will allow precipitation of derivatives. Now, correct me if I'm wrong. Well, actually you can't do that. Let me rephrase that. Sorry if I'm wrong, but I do believe there is another method. What I had in mind was the silver acetylide test, seeing as this test only works on alkynes and not on alkenes or alkanes. If silver acetylide forms when you add Tollens reagent, then it is an alkyne. If not, well, it may be an alkene or an alkane. Please verify this if it is correct. Anyways, moving on. Illustrate with the equation the reaction of bromine and methylene chloride with acetylene. Well, as you can see, that's just plainly it. Although not shown, there are pi bonds that are broken and bromine is attached to the broken bonds. Does toluene behave in the same way like other unsaturated hydrocarbons? Why? Well, the answer is no. It doesn't behave in the same way since it is, after all, an aromatic compound. The electrons are delocalized and move freely about the ring. When reactions do occur, only substitution reactions pass through, which is different from other unsaturated hydrocarbons, as addition reactions can occur. What is the role of concentrated sulfuric acid in the nitration of toluene? Well, concentrated sulfuric acid allows the conversion of nitric acid into nitro ions, which in turn nitrate toluene. Here we see the mechanism of the reaction of the sulfuric acid with the nitric acid. When nitric acid is combined with sulfuric acid releases a hydrogen ion and the hydroxy part of the nitric acid accepts it. The result is a protonated nitric acid and a hydrogen sulfate ion. Since the protonated nitric acid is very unstable, it breaks off into a nitronium ion and a water molecule. The water molecule then reacts with the sulfuric acid molecule, yielding a hydrogen sulfate ion and a hydronium ion. Now, if I am correct, this goes on and on and on until we have a solution of nitronium ions, hydrogen sulfate ions, and water. Moving on to the next question. Show the mechanism for the nitration reaction. Well, this continues from the last question where we left off. The nitronium ion once it comes in contact with toluene or benzene, will momentarily break off a pi bond on the aromatic ring and one hydrogen ion is released. The nitronium ion will then attempt to bond with the ring by breaking off one of its bonds with either of the oxygen atoms connected to it. On the site of bonding for the nitronium ion, the hydrogen transfers to the part where the hydrogen ion broke off, thus stabilizing the ring once more. The hydrogen that broke off earlier will then combine with a water molecule to form a hydronium ion. Now, this may look sort of unstable with charges still floating around, but actually it is quite stable. This is because the molecule is in resonance in which the electrons are delocalized, giving it a lower energy, thus greater stability, than any of its resonance contributors. Moving on. Give the equation involved in the reaction of acetylene with ammoniacal silver nitrate. Well, we've seen this earlier already. To cut it short, hydrogen is broken off and replaced with silver. No pi bonds broken. Result is silver acetylide and nitric acid. Tollens reagent for the silver acetylide test should always be freshly prepared. Why? Well, this is because Tollens reagent has a very short shelf life, and if it is left out for too long, it forms the explosive silver nitride. Thus, if there is unused Tollens reagent, neutralize it first with some weak acid, preferably a mineral acid, before discarding it, as strong acids tend to make it explode. Explain why the terminal hydrogen in acetylene is acidic when in fact the electronegativity values of hydrogen and carbon are almost the same. All terminal alkynes are acidic in nature. This is because there is an increase in the S character. All terminal alkynes are acidic in nature. This is because there is an increase in the S character, making the carbon and hydrogen atom more electronegative by inductive effect, thus acquiring more polarity to show its acidic nature. What test could be used to differentiate carboxylic acids from phenol? Explain how the test could differentiate them. One test that could help differentiate them is the silver nitrate test, because silver nitrate reacts with carboxylic acids to form silver salts. On the other hand, no reaction happens when it is combined with phenol. Why is the order of reactivity of the alkyl halides towards alcoholic silver nitrate tertiary before secondary before primary? Since the reaction is an SN1 reaction, stable carbocation intermediates are favored. Tertiary carbocations in this reaction are the most stable because it is adjacent to 3 alkyl groups, thus dispersing the charge among them. This is followed by the secondary carbocation with 2 adjacent alkyl groups, and lastly the primary carbocation where there is only 1 adjacent alkyl group. The more delocalized the charge, the lower the needed activation energy is. And finally, the last question. In the silver nitrate test for halides, explain why alcohol is used as the solvent for silver nitrate and not water. Water is not the ideal solvent because it is too polar. Ethanol, on the other hand, is less polar and has both a hydrophilic and a hydrophobic part. This makes it ideal for dissolving the silver nitrate where a polar nitrate and a non-polar alkyl chain is present. Well, this concludes our report for qualitative analysis. We hope that you have learned something. Thank you for listening. If you did watch the video,